video notes. Yeah, video notes. Hey everybody, welcome to this edition of Video Notes for Mr. Flugum's AP Chem class. That's right, this is for AP Chem. So thanks for tuning in. If you're looking for a Gen Chem video, it's not this one. This was AP. Well, we're going to be talking about history of the atom and also some other important information that we need to know, just some real basics. So let's go ahead and get started. Alright, so this is kind of that assorted random info, right? You need to know there's a difference between a pure sample and a mixture, right? So a pure sample is something that has a specific atom or molecule. So that would be something like this: elements or compounds. Those are pure samples. Okay. Now a mixture contains particle units of more than one specific atom or molecule. So this might be something like salt water, right? Where it's got water, it's got different salts in it. Okay, or another example might be trail mix, right? Where it's got lots of different stuff together, not specific things, right, that are one atom or one specific molecule, but a mixture of many things together. Well, let's start with this idea of the atom, okay? And it all goes back several thousand years ago to this guy right here, Democritus. He had the original idea of the atom. Alright, now his was just an idea because, of course, Greeks didn't really do science. They just thought about it, right? At least most Greeks anyway. So his was an idea, and even though it was, over 2,000 years ago that he came up with it, his idea really wasn't accepted for a long time. Because how can you accept something that you can't really see? So there's a lot of controversy over the years with Democritus' idea of an atom. Okay, well, along came this guy, Antoine Lavoisier, okay, and his big contribution is this right here. He came up with the law of conservation of mass. And basically, he started burning things and doing chemical reactions in his lab, and he found that the mass before and after was the same, even though that some of that mass seemed to disappear from sight and things seemed to change. So he figured that everything must be made up of matter, even though we can't see those particles. But he wasn't real sure what that was. Then soon after Antoine Lavoisier's law of conservation of mass came along Joseph Proust, right? Just a few years after Lavoisier, and he came up with this law of definite proportions. So through his research with different compounds, he found that pure samples of the same compound always had the same percentage of mass of each element. So for example, we know that water is always this proportion here, right? 88% oxygen and 11.2% hydrogen by mass. And he found that no matter where he got his pure sample of water from. This means that compounds are always made up of the same proportions if they are the same compound. Now the real groundbreaker when it came to the atom was this guy right here, John Dalton. Okay, and he actually came up with a legitimate atomic theory based on evidence from his research. So he made the assumption that elements were made of tiny, invisible particles. Okay, and as Proust did, he thought that molecules would always be composed of equal numbers of each type of element, right? For example, water, right? 2 H's and 1 O, always. Therefore, each element must be made of particles that have particular characteristics. So based on his research, John Dalton came up with 4 particular ideas, or I guess you could call them hypotheses, although here they're called postulates. That's just what the PowerPoint says, I guess. So, right? Every element is composed of tiny particles called atoms, taking the word from Democritus, right? All atoms of a given element are identical, and all atoms of different elements are different. So if you have two oxygen atoms and you put them next to each other, they're going to be the same. But if you take oxygen and nitrogen and put them next to each other, they're different, right? Atoms are not created and destroyed in chemical reactions, okay? So taking that from Lavoisier's work, right? They can be recombined and rearranged, but not destroyed. And then compounds are formed with atoms of different elements combined together, right? So, and as we said on the previous slide, right, a compound always contains the same relative number and type of atoms, giving it unique characteristics. Now at this point then, that means that atoms are solid balls of mass, right? And individual elements are different. Each ball is different for each individual element. Well, we know that's not true. So how did we come to that idea that atoms have positive and negative charges? Now along came J.J. Thomson, okay, in the late 1800s, early 1900s, right? And the cathode ray tube. Now the cathode ray tube at the time had long been known to scientists, but it had remained a mystery. They knew there was this light source that seemed to come from some type of matter, but they didn't know what it was. So J.J. Thomson began to figure it out, and he did it with a relatively simple experiment. What Thomson did is he put an electric field on each side of his cathode ray tube. Okay? And what he found was this: when he put that electric field next to the tube, it changed the angle or the path of those of those particles. And as you can see here, those particles seem to be attracted to the positive side of the electric field and repelled by the negative side. Therefore, that would lead us to infer that those particles would be negatively charged. And since those particles are coming from matter, right? In other words, the electrodes on either side of the cathode ray tube here, then therefore they must come from atoms. So this leads us to something called the plum pudding atom, okay, which is a big circle that is positively charged, right, with small negatively charged particles distributed throughout it. Okay, that's the next step from the solid balls of Dalton, right, to the plum pudding model of J.J. Thomson. So now how do we arrive at this more modern picture of the atom that we have now? Along came a guy named Ernest Rutherford, and him and his graduate assistant, James Marsden, came up with an experiment which they knew was going to kind of happen. So they had a radioactive material in a lead block here. Therefore, since the lead block blocked everything, the only particles that could scatter out came out this way, and they were alpha particles, which Rutherford had determined are much like a helium nucleus. So he knew that they had mass and that they were positively charged. Well, he shot them at a really thin foil of gold. Wanted to see what happened. Now he knew at the time that many of these atoms kind of went straight through, or many of these alpha particles, went straight through the gold foil. But they weren't sure why, and they wanted to know if there was really something that came backwards. Well, what Marsden, who was Rutherford's graduate assistant, found is that there were a small number of particles, these alpha particles, that were deflected at more than 90 degrees. Now what this led Marsden and Rutherford, who took most of the credit, to conclude was that an atom was a space with a very small positively charged solid nucleus in the middle. And this explains why most alpha particles would pass straight through them with only a small amount of deflection, because the positively charged alpha particles will be repelled by the positively charged nucleus in the gold atoms. However, most of the space of the atom was made up of empty space. So that leads us one step closer to the more modern picture of an atom. Now more experiments were to come. For example, we needed to discover the presence of neutrons and their additional mass in the atom. And we also needed to have some more research done into electron levels, right? All these come in due time, and we will continue talking about those in class. Well, thanks for tuning in, folks, and I hope that you have a great day. Stay tuned for a new video coming out this week. Bye-bye.